I welcome Todd Humphreys to the stage and hope you guys will have fun.
Thank you, Michael, and I wanted to thank Neil also for the invitation to come up here. It's really a privilege to be in the middle of NovAtel, Hexagon. You're my people. This is the kind of research that I do, and when I speak today, you'll understand everything, and that's not always the case when I go to give a presentation. I hope you don't understand everything, because then that would mean that I haven't been able to surprise you. My research laboratory is about 7 students, graduate students, a couple of undergraduates, and we are working in autonomy in general, but in the position, navigation, and timing aspect of it in particular. And today I'll be talking about positioning for automated ground vehicles and trying to achieve something like 95% at 50 centimeters. A question you might begin by asking is, how reliable must self-driving cars be? And if you compare them against human drivers, well, human drivers will go 100 million miles between fatalities. A self-driving car might be required to be 2 times as good, maybe 10 times as good, or 100 times as good. It's actually hard to test their capabilities when you're talking about such rare events. Elon Musk says 2 times is good enough, and as soon as you get to that statistic, you should deploy your fleet, because a utilitarian argument says that otherwise you are statistically killing people, and that's what he has said exactly. 100 times is what Ford said in 2019. They did a study and showed that this is the way that you build up trust in a company, and that you can adhere to some of the agreed upon levels that the aviation community already adheres to. Intel and Mobileye came out with a presentation and a document in 2017. They said more like 1,000 times better than human. My own belief is that it's somewhere between 2 and 100 times human reliability. Beyond that, we should just deploy and save these so-called these 40,000 or so people who die every year in North America due to fatal accidents. But supposing we took the lower bound on this, just the 2x human reliability, and ran some numbers like an actuary might do, with a fleet of 1 million vehicles, which is about what Tesla is approaching now, one would expect a vehicle-caused fatality every 5 days. Now, this is vehicle-caused in the same sense that, say, if your steering wheel comes off because of a manufacturing problem, you can trace the cause of this fatality back to some line of code in the software, or some neural net, or some decision that was made by an engineer. And if that's the case, and this is happening every 5 days, you have to ask yourself, would the company's reputation be able to withstand that kind of scrutiny, that kind of negative press? I don't believe so. And not only that, not only would it be negative press, but current product liability law would come into play, and you could sue the manufacturer just as you can sue them for your steering wheel coming off. So there are good reasons why the automotive industry is interested in having high integrity systems, even if the government doesn't step in and establish these norms. Each of these car companies could go out of business if they have fatal accidents like Uber had in 2018 over and over again, and they become the highlight of evening news programs. To achieve such high overall reliability, you'd need to have a risk allocation for each subsystem that's almost infinitesimal. And this talk is going to talk on high integrity positioning, navigation, and timing, something that I'm sure is very familiar to all of you. In low visibility conditions, such as what you might see up here in Calgary on a wintry day, the standard LiDAR sensors and cameras that are commonplace on automated vehicles become either impaired or inoperative. And you ask yourself, well, what kind of sensing can work under these conditions? Some people's response is, you shouldn't be driving under these conditions, not even automated driving under these conditions. But my hope is that automated vehicles can go into areas where humans would be hesitant to drive. And so I'd like to be able to tackle this case, if for nothing more, for the problem that sometimes you might be out on a drive when it was good weather, and then you get socked in with bad weather, and you still want the vehicle to navigate. There are a couple of sensing modalities that work fine in these conditions, and one of them is ground-penetrating radar. This is a view of a spin-out company from MIT that has been experimenting over the last couple of years with ground-penetrating radar. They look only a couple of tens of centimeters under the surface, but they're able to see features that they can correlate with an existing map that they've made, even if the ground is covered in snow or ice. They do have trouble on more porous roads when it rains, because then the radar reflectivity is much different. And this is quite expensive, and it's quite power hungry and fairly large right now. I don't know whether this will ever get to the point where it could be mass installed in automotive vehicles. So I think this is intriguing, but it seems to me that carrier phase differential GNSS is a much better alternative for that particular scenario. Or other techniques like radar-based localization using not ground-penetrating radar, but look-around-you radar. So my talk today will be on these two topics: high-integrity carrier phase differential GNSS, and then radar-based localization. This is research that has come out of our laboratory quite recently, so it's fun for me to talk about it. The second part of the talk, radar-based localization, is a paper that we'll be presenting later next month, as long as they don't cancel the conference. And it's one of our proudest achievements so far. So first, high reliability carrier phase differential GNSS. Our research laboratory, since about 2015, has decided we want to build carrier phase differential GNSS, which is another way of saying RTK or PPP. A lot of these techniques use carrier phase differencing in some way, and this is the most general way of categorizing them. We use this in all sorts of different research projects. We just began to dabble with it, and then we got addicted, and then we got sucked in, and that's basically happened to a lot of people in the PNT world. So, for example, we have built what we call the sensorium. It's this perception module for automated vehicle perception research that goes onto any vehicle we want to slap it on. And it allows us to go and collect data around a city and compare those data amongst the different sensing modalities, and then determine how well we can locate the vehicle or perceive the environment. Up close, you can see that it's equipped with 3 radar sensors and 2 GNSS antennas, a couple of cameras. It's got 3 different kinds of inertial sensors on the inside, and a big computer where we do a lot of our internal processing. We even got a brother for it so that they can collaborate, and this is work being funded by Honda, where Honda is interested in vehicles, maybe not even of the same manufacturer, communicating their raw sensing data, perhaps a video feed or a radar feed or a GNSS feed, so that the other vehicles can benefit and reduce their risk in areas where there might otherwise be blind spots. We like to see how far we can push sensing and precise and high integrity positioning with our sensorium units in the downtown area of Austin. We are interested in both overhanging foliage and blockage due to buildings and multipath. We also have a highly interesting drone program. We built a drone cage on top of a parking garage adjacent to our aerospace department. And in that big drone cage, I get to play with whatever I want to fly there. And I don't have to ask anybody's permission, the FAA or the university, to fly within that cage. And the drones that we've built are quadcopters with 2 GNSS antennas with which we do precise positioning. We do our own receiver design because a lot of the expertise in our lab is software-defined receivers. So on this drone, there are 2 computers. One of them in the back here is actually doing a full carrier phase differential solution on an ARM processor. All of the processing that would traditionally be done in an ASIC is being done on this general purpose ARM processor plus the RTK engine, and all of that in real time for 2 different antennas. And it's pretty impressive to see it happening on a dinner plate-sized drone flying around. That's been fun for us because these can now coordinate with centimeter accuracy and perform things like mapping, coordinated mapping, and other collaborative behaviors. And one of the things that we like to have them do is to fly around and map areas that can be later used in our virtual reality research. So if you can map an area with centimeter accuracy and about millimeter resolution, which is what these drones can do with their 4K images, then you can combine these maps together in a large mosaic, maybe of a building, eventually of a campus, or perhaps even a city. This becomes kind of a one-to-one map. So if you zoom in on Google Earth, you'll eventually become disappointed, right? But if you zoom in here, you get down to millimeter resolution, because not only was the image high resolution, but the drone was flying very close to its subject when it was taking the images. And then this all gets pieced together with GNSS, RTK GNSS as the backbone, so that the map is metric accurate and geodetically referenced. This is fun because then you can put yourself back into the map. You put on a virtual reality headset that has also got our carrier phase differential receiver built into it. And you can now relive the experience of having been in that same spot. And in truth, you are in that very same spot. The walls are in the same place, the ground is in the same place, but now you're the one in control of the visual experience. So if it's night, it can look like it's day, or vice versa. And it's a kind of surreal thing. I finally got this working in late November, just after Thanksgiving in the United States, and I spent 2 hours one morning just walking around in this virtual world that looks a lot like this, except higher resolution, and it was kind of surreal, because I eventually thought to myself, I kind of prefer it in here, it's cleaner, and I can adapt things, you know. And there was a moment where I felt a warming on my cheek, like somebody was shining a heat lamp on my cheek, and I was like, what is going on here? So I finally took off the headset, and I realized that the sun had come out from behind the clouds, and that this was something that wasn't in the simulation, and so it was kind of jarring to feel like there was a disjunction between the simulation and the real world. This is what the headset looks like. Like I say, it looks a lot like the drone, the top of the drone. There's an antenna here, an antenna here, then our front end, and it feeds down to our software-defined receiver module. Is just an off-the-shelf single-board computer. And this is how it sits above the user's head. So this video shows the upstairs drone cage, and my student Ronnie, who's just walking around in this virtual world, checking out to make sure that it corresponds with the real world. It's plenty of fun because you can put entirely virtual elements in the world, or you can just change the coloring or the texture of the true elements. I think that probably has some application going forward for education, maybe for entertainment. I just think it's a fun thing in any case. And you can't do this with the sort of inside-out tracking that is typical for the most recent generation of virtual reality headsets, because the inside-out tracking doesn't typically work in places where the lighting isn't good or the features aren't enough. Whereas this works in any outdoor condition as long as you've got a decent, clear view of the sky. So we call it open world virtual reality, and we're excited to see where it might go. Of course, high integrity GNSS can be used for landing on aircraft carriers, and one of my recent students worked through this with the Navy and came up with some new techniques for tracing the integrity throughout the equations so that we could really ensure that this red spot here, which is the probability that you exceed the so-called alert limit, was below some pre-specified amount. And of course, precise and standard GNSS are different in the sense that when you get a precise solution that is integer resolved, you have a very high probability of getting a tight solution that might be just a few centimeters accurate, but you've got some lower probability that it could be out here in one of these other spots, whereas maybe a standard solution is more Gaussian in its nature. And so you're faced with this quandary of, well, do I take this solution hoping that it's resolved correctly, or and with all of the attendant other risk, or do I accept something that is inherently less risky but higher in noise? To look at this on a log scale, you can begin to appreciate what's going on for customers that care about high integrity. The float solution here might look more Gaussian, and Gaussians, of course, have, on this log scale, the tails really die away. But the fixed solution has an extremely high probability of being very centered near the 0 mark. These are just errors. And yet, out here at the tails of the distribution, you can have accumulated probability that might exceed your integrity limit. And so being able to fix these integers with an eye toward integrity is an ongoing area of research. It's been ongoing actually since the late 1990s, and the requirements are just getting tighter and tighter. High reliability carrier phase differential depends on a lot of things. We like to think of it as critically dependent on a couple of these that are shown here. You definitely want to have multiple antennas on the rover, if you can, for antenna diversity, position diversity. You want to use all signals and all frequencies you can get your hands on. I recommend a dense reference network because this eliminates the effect of ionospheric and tropospheric delays, differential delays that you might experience, and isolates your problem down to only one or two villains. Instead of having to worry about the ionosphere or troposphere, you can just worry about multipath and blockage. And this is mostly with an eye toward deployment in urban areas where multipath and blockage are very difficult. And then, of course, fusion with IMU and vision and radar, fusion with everything you've got is the order of the day. So in the academic literature, there has been a scarcity of papers showing how well high-end RTK systems can work in urban environments. There have been several people published papers in this area, mostly taking 3 or 4 commercial off-the-shelf receivers and testing them and then publishing the results. But I wanted to set a standard for what this kind of paper should look like. And to do so, we put a lot of time into developing our tests and also into developing the metrics that we were going to present to the world in the paper. So these are standard metrics that are well known in the community, in the aviation community, for probability of false alarm, probability of detection, and so forth. And the way that this maps into high integrity positioning is that PV, in this case, is going to be the probability of availability of validated fixed solutions. So this is when you are claiming that a solution has been validated through all of your checks to determine whether this integer adjusted solution has passed all of your internal checks. That's PV. You'd like that number to be high. You'd like it to be 100% so that you're available all the time with these high integrity, high accuracy solutions. Then there's accuracy, and the number to pay attention here is, say, the 95% accuracy of the fixed solutions. If I'm telling you I've got a fixed solution, what's my accuracy? And then there is PS. This is the correct fixing rate for a specified acceptable incorrect fixing rate, P of F. So if I'm allowing there to be, say, 1 in 10,000 incorrect fixing rate, then PS is the rate at which I'm fixing correctly. So among those that I'm claiming to be fixed, what is the probability that they're actually fixed correctly, that all of the integers were resolved correctly? These are standard performance metrics, but it's a little distressing to me that they hadn't been published in these tests that were being performed in urban conditions. Our design philosophy, as we're trying to move into the urban environment, is that we'd like to have control over the end-to-end system. This is something that NovAtel or Hexagon has unique capability in. You develop the receivers that sit at the base stations, the reference stations. You also develop the software. You develop the receivers in the deployed vehicles. It's a nice position to be in because the whole end-to-end solution is something you understand every part of. We adopted the same design philosophy. We wanted to optimize the integrated system, not just some part of it, not just some subset of it. We want to have an end-to-end view of the whole thing with an eye toward improving our probability of our availability and reducing our faults fixing. You can design the subsystems initially for some optimality under, say, Gaussian conditions, but eventually you have to start connecting everything together and trying to improve your design metrics. Also, another thing that you're well aware of here is that fast iteration cycles are critical when you're dealing with difficult to understand environments. Now, carrier phase differential GNSS, I like to say, grew up on the farm. It was first really deployed in a mass market sense for agriculture, precision agriculture. And the lovely thing about precision agriculture is that except when you're driving along the sides of your field near trees or other foliage, you've got a beautiful view of the sky with very few blockages and very little by way of multipath effect. But our idea, our hope, was to see how far we could push this farm-raised carrier phase differential technique into the urban area. So this is the kid who gets restless on the farm, says he's going to move downtown, and now he trades his overalls for some skinny jeans and tattoos. So he's going urban, and that's the kind of RTK that we have been trying to push in our research laboratory. Fast iteration cycles were essential in this case because there's a lot about the urban environment that you can't model, that you can't understand a priori. You have to begin to understand it as you see the data, and there's things that are frankly counterintuitive. There were many changes that I made in our receiver that had a deleterious effect when I thought it was going to be the key, you know. And here I am. I've been doing this for a long time. So my inability to predict what would happen as we moved into the urban environment was humbling for me, and it gave me some, respect for fast iteration cycles and trying to figure things out at least retrospectively. And then our fourth design philosophy is fast carrier recovery. When you're in an urban environment, you don't have the luxury of waiting for seconds or tens of seconds to declare your carrier phase measurement valid again for use in downstream RTK processing. You've got to take advantage of whatever glimpse presents itself. So this is the kind of system that we are trying to optimize. I say it's an integrated system because we develop the front end at in our research laboratory. We use off-the-shelf chips to do the mixing down, and then we digitize them. We put it into our software-defined receiver, which is pulling data from this LDR in the Longhorn dense reference network. And that dense reference network is just a bunch of our own receivers deployed across the reference network, whose software we control completely, so we have access and ability to change that. And then the PPP engine, or we call it the precise positioning engine, pulls data from the precise positioning receiver and from the reference network and produces the precise solution. What's important is that everything in the gray is subject to our optimization. So we wish to tweak anything in the gray box that is required to increase our availability and decrease our faults fixing rate. As far as the designing subcomponents, for fast iteration cycles, the software-defined receiver that we've got is actually quite nice in that regard too, because we can run our testing at many times real time. So the software-defined receiver is able to take in recorded data, but process it at 10 to 100 times the speed that the data were actually collected. And this is nice because we'll all have an idea about another carrier tracking loop, and I'll be able to test it against a whole bunch of different data sets in a short amount of time. And then fast carrier recovery, this last one, I'd like to speak to that in particular. This is the time history for the in-phase in green and quadrature in blue components that are coming out of the correlation of the receiver. This is common, familiar to many of you, I'm sure. But what's fun is to take this time history. It is the lowest level linear measurement. Usually what goes from here goes into the phase tracking loop, and it gets turned into a nonlinear measurement through some sort of an arctangent. And so this is the last thing that's purely linear coming into the receiver. You can correlate the variations you see in a plot like this with the actual events that were happening when you were driving around. For example, this first trauma experienced by the carrier phase was a traffic light overhead, just one of the regular semaphores. And as we passed under that semaphore, there was a bit of trauma to the in-phase and quadrature accumulations. But this wasn't enough to risk a cycle slip. You can see that it never got to the point where I was really going to confuse the blue and the green. However, just after that, there was a building from the south side of the street that was entirely blocking this southward coming signal. And when I say entirely blocking, the signal's propagating through a building. It's probably experiencing in excess of 40, 50 dB. There is no reason you should hope to track this signal. In fact, the best you could hope for is to know that it's being blocked and to exclude it from your solutions going on. But just after we passed by this building, there was this glorious moment, 2 or 3 seconds worth, where the signal recovered and recovered almost, I think, perfectly. I mean, it was basically on the same level as before. And this was a glimpse of the signal between buildings. Now, you might look at that and say, oh, it's too risky to grab hold of that signal and use it in downstream processing. We've got to check its polarity. We've got to make sure that we aren't upside down in the binary phase shift key modulation. And we might want to do some other vetting of the signal. But by the time you've done that vetting, the glimpse is over and you've lost that chance because there was another building just next door. So our strategy was to design tracking loops that allowed us to use those glimpses. And a key idea was to develop techniques for eliminating all of the navigation data bit modulation that modulates these signals, and so that we can recover them without needing to check their polarity. There are other tests that can be run where you can validate this quite quickly within a couple of tens of milliseconds. That's key to urban operation, and this is what's different between an urban RTK receiver and one that's developed for farming, for example. This is a look inside our signal tracking loop, both the phase-locked loop and the code tracking loop, but most of what you see here is the phase-locked loop. I just want to draw your attention, I don't want to walk through this in detail, but I want to draw your attention to the fact that we always are calculating a lock statistic over a variable window. We're trying to get the downstream equipment, downstream processing, as early as we can, an indication of whether they can trust the carrier phase measurement that we're making. We're also sending in modeled Doppler so that the Doppler being tracked through the loop is actually a low bandwidth Doppler. The loop is not required to follow all the variations of the signal, just those that the centralized model was not able to predict. Maybe because it was multipath, maybe because it was signal blockage effects. So this is a vectorized solution driven by a large Kalman filter that operates with the benefit of all the data coming in and then sending back models that are keeping things very close to the code phase and the carrier phase that is expected, so that the local loops only try to pull in something that's already quite close. There are a lot of parameters in a loop like this, though. There's the accumulation interval. So tell me, what is the theoretical best accumulation interval for urban RTK operation? I didn't know, and I don't believe that we've definitely settled on any particular number yet. But my point is, you can't really know that a priori. This isn't something that you can read out of a textbook and recognize that, oh yes, because of the structure of the urban environment, because of the kind of foliage in fall, just after the leaves have fallen, then you should use a 10 millisecond accumulation interval versus a 15 millisecond. No, it's not like that, at least not with our current level of understanding. And just like that accumulation interval, many of the other parameters, there is no obvious optimal choice. So in a sense, you have to run some machine learning on this. You have to test a lot of different parameters and see how things behave, and then try to come up with a model in your brain for how these more optimal numbers are explainable. And this is the process that we went through over about a year. One of my favorite Nobel laureates, Linus Pauling, had a famous quote. It said, if you want to have good ideas, you must have many ideas. Most of them will be wrong, and what you have to learn is which ones to throw away. And he had a lot of good ideas. He got the Nobel Prize for his studies of vitamins. This has application to GNSS also. And the way I like to tweak his quote is as follows. If you want to have good urban carrier phase differential GNSS, you must have many signals, and some of them will be corrupted, and what you have to learn is which ones to throw away. If at any time, I might be tracking 25, 30, 40 signals with the software receiver going through an urban area. If at any time, I knew which ones to throw away and which ones to trust, I could deal with even the worst of urban conditions in Tokyo or downtown San Francisco. But it's not knowing which ones to throw away and which ones to trust that becomes the real challenge. So the diagram to the right is the kind of logic that we have experimented with for doing signal assessment and exclusion. It's probabilistically based in that we start off excluding the signals that already are low elevation or have indicators like the lock indicator that make them look suspicious. But we're willing to do an n-choose-1 kind of exclusion, even an n-choose-2 exclusion, after we've done an initial culling on the basis of probability. This quickly gets out of hand because really you'd like to do an n-choose-m culling of the signals. You'd like to choose m signals to exclude. And then you'd like to change the value of m so that you could exclude more or fewer of them. And at some point, you'll get down to a solution that fits nicely together, whose residuals are good. But because you've had to run so many tests and do so many exclusions, you find that you're doomed to succeed. You're doomed to find a combination of signals that looks good together. And that's just, you know, you've done a study, you've done 1,000 of these now, and the odds are that even if those signals, some of them are corrupt, they will fit together once you've searched so many. So you have to somehow get out of this idea of testing so many different cases to find ones that fit together. You have to be driven probabilistically, and that's what this is doing. It does a first pass and several second passes. A lot of it is driven off of that lock statistic that I mentioned to you earlier. So just to show you a couple of the results that we got from our testing, Austin has an urban core that isn't terribly extensive, but it's growing a lot. This is the downtown area of Austin where we've got the tallest buildings. This is the University of Texas campus. There's our football stadium that can be seen from space. And here's the West Campus corridor, which is a bit more like a European area. It's got narrow streets, fairly tall buildings on both sides, and some overhanging foliage. This is the downtown area. This is the European corridor. And this is our sensorium in action, our experimental setup. So here are some of the results that I'm kind of proud of. Promising first results of these 2 days worth of driving in the downtown corridor through that path that you saw earlier. First, we had 87% availability of validated solutions in the 2 hours of urban driving on each day. And the validated solutions, when they were coming out and stamped as valid, they were accurate to about 17 centimeters, 95%. So our accuracy was quite good. But for high integrity position, you have to ask yourself about the tails, and also you have to ask yourself about the availability. Is 87% availability good enough? What if you're just unavailable for 30 seconds at a time, as we were in the urban corridor? The probability of successfully fixing the integers among these that were stamped as valid solutions was 84% for a probability of failure of 2.4%. So given all of the solutions, 84% of the time we had a valid and correctly valid solution, and 2.4% of the time it was incorrect. And you might look at that 2.4% and say, that's a pretty small number. Don't worry about that. But this is, again, a safety of life system. And even though we were pretty impressed with these results, we didn't imagine them being satisfactory for deployment for ground vehicles. You can see here on the top axis the cumulative distribution function for the vertical and the horizontal. This is where you can see 14 centimeters horizontal and 8 centimeters vertical in the accuracy. You might be wondering, why is the vertical accuracy better than the horizontal accuracy? Remember, I failed to mention that this is being done without the benefit of any inertial sensing. We wanted to do a demonstration of how well you could do with carrier phase differential GNSS alone, with no inertial sensing, not even an automotive inertial sensor, because we wanted to allow other people to use our research and compare their techniques with our techniques without having to worry about variations across inertial sensors. We've subsequently done more data collection where we have 3 different inertial sensors, and we're providing all of those data in an upcoming conference so that people can take on the challenge of seeing if they can do better than the University of Texas in urban RTK. But for these data that I'm showing you here, this was only aided by a model of the vehicle in a statistical sense, not even by non-holonomical constraints of the vehicle wheels. Just kind of statistical model saying you more rarely go up and down than you go left to right and forward to the back. And that's why the vertical is a little bit more tightly constrained. The bottom plot here, though, is quite distressing. The availability gap. There were some times where we had no availability beyond 60 seconds. So we had 60-second gaps in some streets where we didn't have RTK availability throughout that area. So it's promising, but somewhat distressing. I believe it's as good or better than any other published research. No, it's better than any other published research on the topic. And so we wanted to kind of better understand what aspects of our system were providing this improvement. So we did some destructive testing. I learned about this morning with that it's a regular thing here too. But just imagine you've got a cockroach, right? And you want to say, oh, how well can he run if I rip one back leg off? Okay, now how well can he run if I rip his front antenna off too? And you're just trying to better understand the overall system by eliminating certain features of the system. So we did this one at a time for each one of these different tricks that we had up our sleeve. Scenario 1 is the baseline system, the one that was getting good performance, the best performance that we could squeeze out of it. And in the end, as you saw, we had 87.2% of validated epochs with a success rate of 84.8% and a failure rate of 2.4%. So what happens when we start to rip off appendages? Well, I think you'll kind of enjoy this because some of you will be able to appreciate each one of these as perhaps a curiosity that you've had in the past. How much does X affect the overall system when you're trying to do urban navigation? Well, what if X is LNAV and SBAS data bit prediction disabled? So I told you before we're doing wipe off of the 50 Hertz navigation data. We're also tracking WAS signals and doing wipe off of the 2 millisecond, the 500 Hertz modulation that modulates WAS. So if I shut off that capability, it really reduces our availability and drives the failure rate way up. That is a key capability. To do wipe off of these data by prediction or by sending data across a reference network is a key asset to our strategy. Then we looked at scalar tracking with adaptive bandwidth and scalar tracking with a fixed bandwidth. These didn't change things very much. 3% to 6%, a little bit of a benefit of our doing vector tracking with adaptive bandwidth, but it wasn't nearly as striking as scenario 2. What about GPS L2CL tracking in general? We typically track L2C with both the medium length and the long code all taken together. And we obtain a unified carrier phase from both of these codes. But the L2CL signal doesn't have any data bit modulation to begin with, and so there's no need to wipe off that modulation. And we wanted to see if we would do any better with that pilot code instead of the two of them together. It turns out that that has some effect, but not a great effect. Then we looked at age of data. You're getting corrections from the reference network. Of course, the age of the data matters to you. We looked from 200 milliseconds up to a 1 second. And these, again, didn't matter a whole lot except for the WAS signals, which we use routinely for RTK. We found that if you're doing data bit wipe-off at 500 hertz on the WAS signals, so these 2 millisecond symbols that are coming down, you're wiping those off, then each one of the WAS signals becomes as valuable or more valuable, because it's always in the same spot and you can count on it, than a GPS L1CA signal. So exploiting WAS is really a good idea, but the WAS satellites have highly unstable clocks. And so you can only push the age of data out to about 600 milliseconds before WAS becomes useless to you, whereas GPS signals, GLONASS or Galileo signals and others that we were using are useful even out to tens of seconds of age of data. So the age of data here, deterioration was mostly because of WAS. Then instead of less than 4 kilometer baseline, we went to a 14 kilometer baseline to see how that would affect our signals. And you can see that our availability dropped quite considerably and our error rate went up by about a little bit more than double. So a short baseline is important in urban areas, even when you have a lot of signals to choose from, because you're still fighting multipath and blockage, and you don't want to additionally fight anything to do with the ionosphere And since you can do this, since you can deploy receivers across the city and amortize the cost of those receivers across millions of people, why not deploy receivers across the city? And you only need about, say, 3 of them or 4 of them for a city the size of Calgary or Austin. What about if you take out SBAS? So this is removing WAS in our case. The availability drops quite considerably. So that SBAS does help us quite a bit, and we lean on it whenever we can pull these signals in. And then we look at removing GPS L2C altogether and Galileo altogether. Then others like no scored exclusion. In this case, we weren't doing the exclusion technique that we had developed, and our availability drops there. Our failure rate doesn't go up much, but our availability drops quite a bit. And then the last one is antenna calibration. We calibrated the antenna's phase centers over a period of days and got very good maps of how the phase center changes with elevation angle. And that does improve, or if you don't do that, it increases your failure rate. So these are, I think this is a quite useful table in the paper that we created so that you can get a sense for where you're buying yourself various parts of your total integrity budget. So the takeaway I would have is that with data bit wipe-off on LNAV and SBAS and a dense reference network, it is now possible to develop a standalone, unaided, so this is no inertial system involved at this point, single antenna RTK pipeline. We had 2 antennas on the vehicle, but we were only using 1 of them for this research. That achieves a successful fixing rate of 84.8% for an incorrect fixing rate of 2.4% in a deep urban environment. So that concludes the first portion of my talk, and I will quickly go over this radar-based localization stuff too, which is a little bit more hot off the press. The radar we're working with here is not one that spins on the top of your car and gives you this lovely view around the vehicle. It's automotive radar. It has 2 major failure modes. One, the data you're getting back for each scan is extremely sparse. And secondly, it's full of clutter or missed detections. So anybody who has worked with automotive radar realizes that it's a really valuable sensor because it penetrates snow and fog and rain. But it's a terrible sensor to work with just because of the lousy data that you get back. And yet, it's deployed on almost all production vehicles now. It has been commoditized, and there's a real reason to lean on it if you can. And our goal was to see how well we could do in obtaining positioning for our vehicle based only on the radar data and on some mechanism for odometry. On the right-hand side here, in this middle plot, this is what you get back on a particular scan of 3 radar units combined together. So at about 10 hertz, you get a scan that looks like this. Now, somebody who's involved with image processing might look at that and say, wait, I can't use my traditional techniques of feature extraction and mapping. And that's true, because the sparsity of the radar data doesn't really allow you to recognize stable features that you might make correspondences with. Even when you combine 5 seconds worth of the data, feature extraction and mapping and matching might not be possible, but you certainly start to see features of the environment that you could correlate with a prior map you had built of this same area. So this is what happens when you drive through the area repeatedly, and this is what happens when you combine 5 seconds worth of these individual scans across 3 different automotive radar units. And this you could look at and say, well, there's a chance there, right? I can see features from the main map over here, and now it's just a question of correlating against those and justifying your techniques and trying to make them closer to optimal. So the first stage in this kind of research is to do a mapping session. And you might have, as we did, a high-end mobile mapping unit that allows you to determine your pose, the vehicle pose within a couple of centimeters. Or you might simply do mapping on a good, bright, sunny day, in which case you can use your cameras to help to overcome any gaps there might be in your GNSS system so that you can lay down a radar map that is metric accurate and accurate to about 10 centimeters or better. And so this isn't something that has to be done with special purpose vehicles. This can be done with the actual vehicles that will later ingest the map. It can be crowdsourced. But the crowdsourcing would happen on the bright sunny days, and the map would later be used in periods anytime later, such as in periods of inclement weather. Then on a second session, in our case on a separate day, This one was done on a weekday with lots of cars around. This one was done on a weekend with a lot fewer cars, so that we could compare the performance, or so that we could assess the performance when the environment had changed quite considerably. That's when we go through and do our localization session, in which we're taking little fragments and trying to match them to the original map. What I wanted to draw your attention to in these maps is a particular feature of the urban environment that prevents you from using more naive approaches for determining your location with radar map matching. And these features are regular patterns that show up in the urban environment. Why? Well, because cars are often roughly about the same size, and parking spaces on the side of the road are all the same size, and so you get cars parked in those parking spaces, and you can get an off by one error in which your fragment, your map fragment that you've created locally on day 2 correlates nicely with the original map on day 1, even if you're off by 4 meters along track, you see. And this is just a characteristic of the urban environment that you have to keep in mind, because if you're doing iterative closest point or techniques like that that are gradient descent searches, you can easily get caught in a local minimum that might be off by 1 with respect to a global minimum. And you can show that this is happening in the data that I'm showing you here. This is from the original full map, and you can see some vehicles parked at the side of the road here. This is from the fragment that was created on the, say, subsequent day, and it has some vehicles to the side of the road also, or some pattern that might not even be vehicles. And over here you can see the corellogram in the north and east direction. Anytime you see the brightest spot, that's where things fit most closely. And in this case, it's an offset, so we're looking at the errors. The bright spot being very near 0, 0 is a good thing. Any deviation from 0, 0 is the error that we would experience. But notice there's a lot of alignment along the long track direction. That means that there isn't great observability along track. And there also notice that there are a couple of local minima here in the along track direction, just where you'd expect to be off by 1 parking space. Now, this matters because if you throw, like I say, some of these other techniques that have been developed over the many years for visual and for LiDAR point cloud matching, you will fail. You will get caught in the local minimum, and you won't have the robustness that you need for a case where your prior position wasn't highly accurate. Now I'll get to show you a video. On the left panel, you'll see this corellogram moving in real time as the vehicle goes through the urban environment. Over here, you'll see the full map, and over here, you'll see the fragment of the map that's created on the next day. Anytime you see the yellow dot offset from the 0, 0, that's an error. Or if you see other features here that cause periodic behavior in the corellogram, that's a place where we could have gotten caught in a local minimum. And so there's a lot of driving and a lot of different circumstances that you face in an urban area, but thankfully the yellow dot does remain mostly fixed around the 0, 0 spot. And if you're doing the kind of global search that we ended up applying to this based on Fourier transforms and very fast correlation, then you can avoid the pitfalls of getting caught in one of these local minima. The takeaway here is explained in this plot. This is a complementary cumulative distribution function, also called a survival function. The idea being that at a horizontal position of, say, 40 centimeters here, you can look up and find out what percentage of the data, what percentage of your solutions was greater than that 40 centimeters. And what we found then was that we could hit a 95% error rate at less than 50 centimeters in translation. And then the green line is for heading, because we have to do a full rotation and translation to put the vehicle in alignment with the original map. So we have heading here that turned out to be better than about 0.6 degrees, and horizontal positioning that was at 95% better than 50 centimeters. This is the very best positioning that's ever been discussed in the open literature using automotive radar and without any kind of other fancy sensors that are being fed in. I will say that in order to get these results, we had to have some stable odometry that would allow us to accumulate the radar scans over the 5-second interval. And we looked at various different ways of doing this with inertial sensing at automotive grade. It's not so great. At industrial grade, it does quite well. And then radar odometry itself does quite well. So there are several techniques that you can use to determine your vehicle's trajectory over the 5-second window stably enough to accumulate these into the fragment that you later correlate with the map. But apart from that kind of odometry, this is exclusively radar. And it's radar that's off the shelf, commercially available. So between radar and carrier phase differential GNSS, it seems to us that we can offer 50 centimeters, 95% positioning with nearly perfect availability in urban areas and outside urban areas. Remember that when you're out in an open field and there aren't any radar reflectors from which you can correlate against an existing map, that's where GNSS works well, right? And deep in an urban canyon where GNSS is struggling, the radar comes to bail you out. So between these two technologies, we think that there's a good chance that you can get very high integrity positioning for automotive vehicles going forward. I'll conclude there. Thanks for listening.
Thanks, Todd. See, you have a professional teacher here. They're always on time. We have time for Q&A. I started off with my question.
Sure.
On your first example, the RTK you used, was that networked RTK or single base station RTK?
It was ultimately networked RTK only in that we could switch between base stations, but each one was individually being done with a single baseline.
So you didn't model a virtual
We didn't
base
try to
station.
model the ionosphere there. We were close enough we didn't have to. The Longhorn dense reference network has been set up so that it can be done with network RTK and ionospheric modeling. But we just have been so lazy and so preoccupied with multipath and blockage that we haven't worried about that. When we use a single baseline solution with a short baseline, it just doesn't matter.
Okay, thanks. First question?
Where are you getting the data for the data wipe-off?
The receiver itself generates most of that. So the inside the receiver we have GPS L1CA, so the LNAV prediction engine. The LNAV data are about 99.8% predictable. There are a couple of gotchas that come down, mostly sending military keys down over certain segments of that cannot be predicted. Otherwise, it's entirely predictable. So we have isolated those segments, and we have a flag that says, look, I'm giving you a prediction in this segment that is less predictable, so you're going to reduce your reliance on my prediction for wipe-off. We can also send it over the network from the other GNSS receivers that have a better view of the sky. And in the case of SBAS, that's what we have to do. We looked for a long time at patterns of SBAS data bit modulation and found out we just couldn't quite make sense of it. And then I visited Todd Walter at Stanford, who was the father of SBAS, and I said, why is this not predictable? It should be, you know, you're sending out a lot of repeated data. And he said, oh, the way it was implemented, don't even try. So in that case, we are sending it over the network. And those data come by and get wiped off. Every 2 milliseconds of data gets wiped off there.
So what about when you're having an ephemeris changeover or an almanac changeover? Are you trying to predict those bits also, or
No.
you just coast through that
No,
section?
it's 18 seconds where we're exposed. And we do our best to do standard Costas loop recovery during those times, and then we go right back as soon as we can to wipe off and full carrier recovery.
How do you recognize when you're switching over?
The switchover is highly regular, every 2 hours.
Okay.
First 18 seconds, every 2 hours, you're exposed.
So if they come out with a ephemeris at an odd time.
Okay, so the ephemeris always comes out every 2 hours. The almanac data can change even between those boundaries. And we have a mechanism whereby we detect changes in the almanac and then clear out the almanac data for until we have built up enough confidence in the new almanac data to go back to wipe off. That happens rarely. The almanac data are almost always switched out at the 2-hour boundary also, but not always. It took us a long time to look at all of the statistics of this, and yet I think it was worth the effort.
On your slide with the pulling off the appendages,
Yeah.
when you pulled out Galileo measurements, it looked like the
Yeah, it got
failure
better.
got better. So did that indicate that the Galileo was causing those false fixes or incorrect
What that
fixes?
really indicates is that I'm not lying to you on that plot at all, because I would love to cover up that result. The truth is that the Galileo satellites, we were only tracking 6 of them, and they were all somewhat low elevation. And so by excluding them all, we just ended up with better integrity in the end. That is not an indictment of Galileo in general, and I love Galileo signals, but it was just a hallmark of this 2-hour data set that we were showing. Yeah.
So you mentioned that it's key to distinguish between good and bad signals. So which metric did you use to reject bad signals? So, I mean, practically elevation is one of the,
Right.
or CU not, or
Right.
Okay.
So we have a kind of score that is built up on the basis of elevation angle, carrier to noise ratio, and the lock statistic, so the carrier tracking lock statistic. And this score is effectively a heuristic that I put together and found worked quite well. It starts with the low elevation signals. And remember, I don't have to be perfect with this, because this is just the score that I use to determine which one I'm going to throw off the island next, vote off the island next, okay? So I go through and I eliminate signals and check how the remainder hang together. If you do a guided search in an n-choose-1 fashion or an n-choose-m fashion, you can eliminate the many forking possibilities that would have doomed you to successfully finding a well-fitting ensemble. So it's very important to do a guided search, and these are the 3 metrics that we have found were the most informative for the guided search. And we weight them differently. The carrier phase lock detector is actually weighted highest. Yeah.
Okay, so when you compared it to Septentrio, did you tune it in real time, or in post-processing to find the best signal?
So the way we did this was that I had several days worth of data, right? And I was able to tune it to my satisfaction on 1 day's worth of data. Then I deployed that same tuning on the 2nd day's worth of data, and that's where we made the comparison against Septentrio. So yes, I was fine-tuning lots of stuff on the 1st day, but I didn't cheat in tuning for the final case, except to the extent that we increased one of the metrics that forces our faults fixing rate to go lower. And so we went lower until we matched their faults fixing rate, and then we looked at availability. And ours exceeded theirs by about 20%.
So your system is dual antenna, but you only used one for your GNSS results. Do you
Just
only
for these results that I'm presenting here, because I wanted them to be easily replicable.
Okay, so do you only use dual antenna with the inertial integration, or do you get advantages from it with GNSS only in some cases as well?
Oh, we get advantages with GNSS only. If you're only taking advantage, for example, of the constrained baseline knowledge, you can reject solutions that don't fit. You could reject both of them when they don't fit. And you could also take advantage of the 2 solutions for standard positioning. There's a great deal of benefit to having multiple antennas for diversity in these urban areas. And there are a whole lot of different ways that you can exploit that diversity. We haven't made any claims that what we're doing is yet optimal.
So a lot of what you're describing here is every car for itself. One car against the world, but early on you talked about your sensorium and collaborating. So when you look 20 years down the road, what do you see for broad deployment of autonomy? Do you see a lot of collaboration between cars, or maybe deployment of infrastructure?
I want to make sure that every car can fend for itself as regards PNT, no questions asked. I don't want to depend on any other vehicle or even infrastructure to tell me where I am. However, for the perception problem, I don't think it's possible. I don't believe we can eliminate blind spots with ego sensing sufficiently to reduce the risks down to levels that I would consider tolerable. So My view is that for the perception of other collisionable objects, soft targets like humans or dogs or motorcycle drivers and other vehicle targets, there is really no way of getting the risks down low enough without collaborative sensing, whether it's infrastructure or other vehicles. So I'm capitalist when it comes to PNT and communist when it comes to perception.
You had a plot of false or failures for RTK. How did you develop that model? Is that based on you sensing the environment and trying to model all the errors and then accumulate it that way, or?
Well, the plot that I showed was a position domain plot, or unless you're talking about the table, is it?
Where you showed the difference between float and fixed.
Oh.
So when you're going, like, trying to do these computations on what your safety is,
Mm-hmm.
how do you handle non-Gaussian errors?
Yeah, it's a good question.
And and especially with GPS, do you treat multipath as a Gaussian error, or is it fixed in some locations
Right.
and systematic? Or?
I think these are some of the most intriguing questions for research right now. The plot that I showed you was an outgrowth of the research that my student Nathan Green was doing with the Navy for landing of UAVs on carriers. In that environment, apart from a little bit of multipath that comes off of the vehicle itself, it's highly Gaussian. It's kind of a beautiful open sky condition. And so what I was showing you were actually just computer simulations of the probability distributions under the Gaussian assumption and their position domain effect of various faults fixing. I would dearly love to have a diagram like that for urban RTK. And we can kind of get it for the position domain effects when we compare it against a truth solution like the Atlans that we were using. But we can't, even in 2 hours of driving, probe those tails nearly at the fidelity that I was showing you. That was a log plot, right? And so it's hard for me to talk about overall integrity in the multipath-ridden and blockage-ridden urban environment. And yet that's one of the environments where integrity will matter most for automated systems. So I'm thinking of that as job security going forward. That's going to be a tough nut to crack.
Not just you.
Yes.
Not just you.
Right.
Just with regards to the car-based radar, how immune will that be if every single car is blasting out radar? How well will they work in that environment?
So FMCW radar units like these, this is frequency modulated continuous wave radar. They chirp over a very wide bandwidth, about 2 gigahertz bandwidth chirp. And only if your chirp and my chirp happen to collide in the frequency space would there be significant interference. And you can work this out and look probabilistically at the densities that would be required. And the truth is that it will get there. We'll get there to where this kind of radar would begin to fail due to interference. But when that happens, what we can hope is that the FMCW waveform has been modified to incorporate some sort of a spreading code itself, which will give it some immunity even to radar spoofing, which is not currently a problem, but neither was GPS spoofing back in 2008. Yeah. So radar spoofing could be mitigated by having a coded signal chirping, and so can interference in general. And so you can have plenty of vehicles in the same vicinity that are broadcasting on the same frequencies.
So you mentioned that you're using machine learning to adjust the integration time.
Oh, I shouldn't have. It was this machine. Okay. I recognized while I was tuning this that I could have handed this over to a genetic algorithm, for example. That there was a lot of try and try again, and let's see what this happens and what happens here. There were a lot of parameters to tune, and I ended up doing a lot of unidimensional tuning. I would get things to work well, and then I would tune one of them until it maximized the statistic, and then I would tune the other and maximize. I don't pretend that this is an optimal way of going forward, and I do think a machine learning approach might be profitable in these cases where you understand so little about the probability distributions of the environment. But yeah, I didn't turn this over to a neural network except the meat one in my head.
Where do you see the role of machine learning in navigation, for example?
As little as possible. I believe that machine learning is fundamentally useful for vision systems and image processing, where you don't have good statistical models. You don't even know how to begin making a statistical model for hot dogs in images, with all of their different coloring and their different attitude and different amounts of relish. But when it comes to PNT, it should be a last resort. Let's exhaust the other techniques that we've learned that are optimal, and let's leave the machine learning to pick up what we couldn't do. So I think it would be profitably applied in trying to help me decide what parameters to choose for an urban environment. I don't think it's profitable for me to hand IF samples to a neural network and ask it to pop out positions. I think that's silly, and yet some people treat machine learning as the antidote to problems even of that nature. I'm more skeptical, and I've been approached by, my research group is often approached by businesses that say, look, here's our problem, and we want you to solve it with machine learning. And you'll appreciate this. One of the recent problems was one where we were just trying to estimate the lever arm between a GNSS antenna and an inertial sensor. And they wanted us to do it with a neural network. And I said, but no, you don't want to do this with a neural network. There are good adaptive Kalman filtering techniques or augmented techniques to do this. And they said, nah, because our people that are incorporating these techniques don't want to have to be a PhD and know adaptive Kalman filtering. They just want to have a neural network that they throw at the problem every time. And so we went through the motions and showed that the neural network was abysmal at estimating the lever arm, whereas the Kalman filter was just fine. I find that that's sort of the mentality today, that people believe that they can reduce the requirement for education of their workforce if they just have ever more sophisticated neural networks. But hold on, these neural networks need a lot of care and feeding. And a lot of them are so sensitive to the parameter choices in the network, the number of layers and what kinds of regularization you apply and what kinds of nonlinearities you apply, that you either need a PhD or a whole lot of time just for that. So my view is go as far as you can with model-based techniques and then appeal to neural networks.
Okay. Thank you, Todd.
Thank you.
Because you are heavyweight in GNSS and PNT, we decided to give you a heavyweight gift. Little thing to remind you of your presentation here today.
Wow, what is
I'm
this?
not allowed, it's a 3D laser engraved heavyweight for your desk.
Whoa, it's of the ship that we spoofed. Isn't that amazing?
Exactly.
Oh boy, I've got to use two hands.
Supposedly not too allowed to take it out without the gloves, but I just do it now.
Okay. Holy smokes, that's so cool. Huh. Well, I'll put that on my desk. Todd Humphreys, we
will check.
are grateful for your visit to the Hexagon Calgary campus. Your contributions will inspire our team to ensure that your vision to protect and grow GNSS is carried on for many years. Thank you, Michael. That's really a great gift and unique.
We'll ship that to you. You have to put that in your carry-on and explain to TSA what that might be. Thank you, Todd.
Thanks a bunch.